Hi, my name's Fred Zelt. I'm a geologist and cyclist living in Pittsburgh, and this talk will be about the geology of Western Pennsylvania with a special focus on the Laurel Highlands and two great bike trails in the Laurel Highlands. So let me share my screen, get the talk going here. These two bike trails will be a focus of excursions hosted by Venture Outdoors and Earth Science Excursions in 2022. They're part of the 22 and 22 theme. There are actually three more, so 25 total bike trails longer than 10 miles in Western Pennsylvania. And each of these major bike trails will have a ride hosted by Venture Outdoors in 2022. And the two that are the focus of this talk are a section of the Great Allegheny Passage and the Indian Creek Valley Bike Trail, which are highlighted in green on the map and are also highlighted on the list. And these 25 bike trails in Western Pennsylvania, we've organized into 6 geologic themes, areas with similar elements of geology, relationship between the landscape and the geology and type of landscape that's there. We've recorded a talk and shared it already for the area outlined in blue on the map, the Allegheny and Ohio River valleys. There's also been a plateau talk, the area outlined in black. And we've shared a talk for the Conemaugh uplands and the bike rides that are circled in orange. So this focus area of this talk is the area highlighted in green. But some elements of this talk are going to apply to all of Western Pennsylvania. Each of these talks has a bit different geology theme so that they don't repeat a lot of the same content. And the purpose of sharing this and creating this is to provide some background for the people on the Venture Outdoors bike rides, but we're sharing it publicly just to give people a greater understanding of the landscapes and their geologic underpinnings in Western Pennsylvania, and to highlight the 25 great bike trails that are in this area. We're not sharing this publicly to sell tickets for the Venture Outdoors rides. We've had 3 of them already, and the rest are all sold out. So that's not the purpose of this. The purpose of this is to highlight the great trails in this region and why the land is shaped the way it is, and a bit of the history. The 2 bike trails highlighted in this talk are a segment of the Indian Creek Valley Trail and a part of the Great Allegheny Passage. The objectives of the presentation are to increase awareness of the link between geology and the shapes of the land in Pennsylvania, including a focus on the Laurel Highlands, and to give some background on the 2 great bike trails that are a focus of this talk as well. And to get there, first we'll introduce the segments of the trails that we'll be cycling. We'll talk about rock types and ages in Western Pennsylvania, talk about the way the land is shaped, how that expresses the underlying bedrock. And then there's a special section on interpreting trace laminations in sandstones in terms of which way the water flowed that deposited the sand grains that became the sandstones. So agenda items 3 and 4 are special to this talk, but they have broader application across Western Pennsylvania. Introducing the trails then, first we'll talk about the Great Allegheny Passage, 150 miles between Pittsburgh and Cumberland. And the part of it that we'll focus on here is the highest part of the Gap Trail, the peak of the passage, from Meyersdale through the Big Savage Tunnel to the Great Overlook to the east. So that's the segment we'll be focusing on. Here's a picture from that segment. It's a great crushed limestone trail, very well maintained, beautiful place, this picture from autumn. And here's an elevation profile for the Great Allegheny Passage, plus the C&O Canal towpath, which connects with the Gap Trail in Cumberland. And here you can see the part of the Gap Trail we'll cycle, starts in Meyersdale, goes across the Eastern Continental Divide, and then down the other side a little bit to that overlook that I mentioned. Here's a map of continental divides in North America, and the one of interest to us is the gold line, The area where we'll be cycling here is in southern Pennsylvania. And the gold line here, that continental divide, separates rivers and streams that drain into the Gulf of Mexico from rivers and streams that drain into the Atlantic. And here's a picture of the continental divide on the Gap Trail. There's a road overpass here, so there's a portal. And here's a picture from early springtime, and certainly a trail that's inviting you to come explore it. Here's a map of the watersheds in the United States, the lower 48, the Mississippi Valley, Mississippi River drainage, Ohio River drainage, draining off to the Gulf of Mexico. So that's to the west of the Continental Divide. And then to the east of this Continental Divide, drainage is going into the Atlantic, and specifically the streams to the east of the Continental Divide where we'll be drain into the Potomac. There's another picture of the Eastern Continental Divide. And you can see the outside of the portal here. This is a favorite place to stop and take pictures. In fact, this highest part of the Gap Trail is many people's favorite part of this very popular trail. Another feature of this segment is the Big Savage former railroad tunnel. It's well illuminated inside, although it's still good to have a headlight. Last time I was in, one of these lights was out and it made that segment pretty dark. And here's a cyclist popping out of one of the portals. And when you come out of the portal on the eastern side of the tunnel, this is the view that you see. We're heading off to a big overlook. This is the best, longest overlook on the Gap Trail. For many people, a real highlight of a 150-mile ride on the Great Allegheny Passage. And we'll come back and talk about the view here and what you can see after we've introduced the geology of the area. The other trail that's a focus here is the Indian Creek Valley Trail. It's in two pieces right now. The green here is a part of the trail that's in the upstream area. It goes along the river, the creek rather. And then the part that we're going to cycle is circled in red, and it goes from Indian Creek Reservoir down to the Youghiogheny River and into the Youghiogheny Gorge. So that's the part of this that'll be a focus for us, and that's the part we're going to cycle. Here's an elevation map. We'll see a whole series of these. The higher elevations are white and reds. Lower elevations are blues and greens. And this map, you can see Connellsville here. There's Confluence. There's Chestnut Ridge. There's Laurel Hill. And in between those, the Youghiogheny River cuts through this highland area. And so in between Connellsville and Confluence is the Youghiogheny Gorge. Indian Creek is right here, the tributary. So the stream comes down into the Youghiogheny Gorge. It has its own gorge on the way down in Indian Creek, going down from the reservoir. The town of Ohiopyle and Ohiopyle State Park are in the valley in between Laurel Hill and Chestnut Ridge. That's where the town is. Here's a perspective 3D view of the lower part of Indian Creek and the gorge. There's the reservoir where we'll start cycling up here. We'll go on the side of the Indian Creek toward us. That's where the bike path goes. Here you can see the picture of the bike path. And this valley has no road in it, this segment. So it's very quiet. You're away from road noise. It's all nature. It's just a great place. And the stream, that's the main sound you can hear, is rushing water in small waterfalls and cascades as the stream makes its way down into the gorge. The Gap Trail's on the other side of the Youghiogheny River, and in between is Camp Carmel, located here. This is a geologic map of that part of Indian Creek. There's the reservoir. There's the creek coming down to the Youghiogheny River. The fine lines here are from a topographic map. Those are lines of elevation. So here's a high elevation going down into the stream valley and then climbing up higher elevation away from that. And the high elevations here, the color indicates a rock layer, a youngest rock layer around here of bedrock. There's an older bedrock layer, an older one still, and older sedimentary rock layers as you get down to the bottom of Indian Creek. These top three are Pennsylvanian in age, and the bottom two are Mississippian in age. Some of these have some pretty well developed quartz-rich sandstones in them that help hold up the small waterfalls and cascades in the Indian Creek Valley. This is a picture of the reservoir dam. We'll visit there, and there's a nice cascade on the downstream side of the dam. And then there's that picture from the trail. This time you can see it a little bit better. Nice rapids down there in Indian Creek as we follow along and can hear that. And it's just a great place to enjoy being outdoors and enjoy nature. Here we are at the mouth of Indian Creek, where it flows into the Youghiogheny River. And there's a stone arch railroad bridge here that's still in use. There's another bridge that's not in use now. And across the Youghiogheny is Camp Carmel, as I mentioned, and we're in the Youghiogheny Gorge down here. So it's just a great place. Because it's a one-way trail, there's not through traffic. It's a pretty quiet place too. Now let's talk about rock types and ages. And to start off, I wanted to establish a relationship between weathering and landforms and rock types, sedimentary rock types especially. And we'll use an example from the Grand Canyon. Geologists love dry areas. We love studying those because there's no soil and plants covering up all the rocks. And here's a quartz-rich sandstone. It's a cliff-forming unit, and so it's very resistant to erosion. And there's a shale loaded with clay that's a lot easier to erode. And so looking at more of the Grand Canyon, you can pick out these sandstones resistant to erosion. You can pick out shales that are forming slopes here, not resistant to erosion. And in Grand Canyon, actually, one of the cliff forming units is a limestone. In Pennsylvania, limestones dissolve in rainwater and groundwater, so they're not typically forming the tops of cliffs or mountains. Sandstones usually are doing that, and limestones often are in the valleys along with the shales because they're less resistant to erosion. Now let's talk about the rock types in Pennsylvania, northern and western Pennsylvania. The drawing here is a cross-section from north central Pennsylvania to western Pennsylvania, and vertically from old rocks, 500+ million-year-old rocks down here, to younger rocks, still hundreds of millions of years old, but younger rocks. The colors indicate the different rock types. A key one is sandstone, so made up of sand grains. And here's one of Silurian age that in places is very quartz rich. It's up to 95, 97% quartz. So, and if you hit it with a hammer, the hammer will ring. It's very hard, difficult to erode. And that's a ridge forming unit, and one that we'll talk about later. Here's an Ordovician limestone that forms valleys, and soils based on that limestone are really excellent for agriculture. So here you can see an area of wall-to-wall croplands because of that Ordovician limestone being near the surface. There are a couple more sandstones up here and of Mississippian and Pennsylvanian age, quartz-rich sandstones. Those tend to be ridge formers also, and we'll see that. There's another limestone, this one Mississippian age. We'll have a special focus on the Loyalhanna Limestone toward the end of the talk. Other colors that are on here, red are red beds, and here in the Upper Devonian age, these red beds include lots of shales that are red, as well as sandstones that were deposited by river channels. There also are sandstones on deltas where the rivers met an inland seaway, and the white here indicates offshore marine shales. The gray are organic rich marine shales with lots of algo-organic matter in them. And this one of Middle Devonian age, that's the Marcellus. The organic rich marine shale of Ordovician age down here, that's the deeper shale gas target, that's the Utica. There are lots of other rock units in here. There are some limestones of Lower Devonian age and Upper Silurian, early Devonian and late Silurian ages, and we'll refer to those briefly. But the ones that are highlighted are really the ones we're going to focus on. When you come up into the Pennsylvanian, you can see these black bands are meant to indicate a couple of the prominent coals. There are a lot of other thin coals as well. The medium blue indicates some marine limestones that are up here. There also are non-marine limestones and both marine and non-marine shales. And those thin limestones in the middle Pennsylvanian are enough to make some soils that are pretty good for agriculture. Maybe not quite as good as the ones based on the Ordovician limestones, but pretty good for agriculture. And you'll see that when we talk a bit about land use. Here's a perspective of Earth during early Ordovician time, 480 million years ago. And central Pennsylvania would have been here. It's on a continental margin near the equator, a great place for sea life and for lots of carbonate sediment to accumulate. And when it was buried, become rock and become that Ordovician limestone that's so great for soils in central Pennsylvania. This is another view of Earth, and there's been a continental scale collision at this time in the late Devonian that's raised a mountain belt. Here's an outline of Pennsylvania. There are rivers flowing away from the mountain in this coastal plain area, coming and making deltas on the edge of an inland sea that would have had clay and shales deposited in it. And in the coastal plain area especially, but many of the rocks in the deltas too, are especially red. So this is that area of red beds that we saw on the cross section. And the streams, as you can see, would dominantly be flowing more or less from east to west. Similarly, during Pennsylvanian time, Mississippi and Pennsylvanian times are called Carboniferous worldwide. There's a mountain belt here because of continental scale collision between this part of Africa and this part of North America. And there are sedimentary basins flanking that mountain belt where lots of sediments are accumulating. And being close to the equator here, some of those sedimentary basins had thick peat deposits form that when buried formed coals. So that's why the Pennsylvanian and Mississippian are called the Carboniferous, because there are so many coaly sediments then. Also, there are assembled continents near the South Pole. And as you'll see when we talk about climate, this was a time when there were glacial, interglacial periods like there have been in the last couple million years or so. So it was a time of glaciations, but there weren't any glaciations here where Pennsylvania is. It was very close to the equator. This is meant to be a map of depositional environments going from that mountain belt about 300 million years ago during the Pennsylvanian off to the east, and then rivers flowing to the west across the coastal plain into this inland sea, so that if you would find sandstones that were deposited in those river channels, the dominant flow direction should be more or less east to west. You can see some other environments here, alluvial plain where there would be clays and silts deposited, maybe some sand splays, inland or freshwater lakes could leave behind freshwater limestones. If the sea flooded in, you could have a marine limestone that would flood in and overlie these coastal plain deposits. And there are some deltas where you might have delta mouth sands coming out into the sea. The ages of the rocks that we'll see in the Peak of the Passage area are Upper Devonian into the Pennsylvanian. So they're 300-ish million years and older. These divisions between the ages on the bottom here are 10 million year divisions. So pretty old rocks. The rocks, as you saw on the map that we'll see in Indian Creek Gorge, those are a little bit younger. They're Mississippian and Pennsylvanian. So those are pretty old rocks and they cover quite a span of time. But in terms of Earth history, not a huge fraction of it. Earth history goes back more than 4.5 billion years. And I mentioned climate. So here's an introduction to paleoclimate that goes back 500 some million years here. And I'll talk a lot more about paleoclimate and the basis for this proxy measurements of estimates of ancient temperature of Earth. I'll talk more about that when we talk about the glacial theme because it's very relevant there. You can see 5 degrees Fahrenheit on this scale. On the left-hand side, 2 degrees C. And the last 12,000 years, we've been in an interglacial period, but 20,000 years ago was the last glacial maximum. So there were glaciers that came all down through Canada into Western Europe and into Russia too. And when those glaciers largely melted, sea level rose about 120 meters. And you can see the scale here. This is only 5,000 year divisions. These are 200,000 year divisions, so it's more squeezed. And there have been lots of glacial, interglacial alternations for the last 2.6 million years. Earth has been at times much hotter than now. For example, when dinosaurs were around, Earth was hotter. There were ferns growing at the poles, for example. But there was a time about the age of the rocks that we'll see around 300 million years ago that is thought to have been about as cool as now, and also had glacial, interglacial alternations and sea level rises and falls, similar to what has happened in the last 2.6 million years. And here you can see the ages of rocks along the routes that will cycle on the Gap Trail, the peak of the passage. There's a little close-up of that. The divisions here at the bottom are 100 million year divisions. So this is a pretty smooth sort of profile. There would have been a lot of detail in this actually. And there's Upper Devonian into Carboniferous ages of the rocks that we'll see on the peak of the passage. Going from a hot climate on Earth in general to a colder climate, again with alternations, surely within this time. And the types of rocks here, this is where there were the Devonian red beds in that time of generally hotter climate, a very different climate. There's a Mississippian marine limestone, that's Loyalhanna Limestone, we'll talk about later. And then there are actually coals of Pennsylvanian age deposited near the equator in peat swamps, so a very humid, temperate, at least, environment. So these are kind of indicators of the big change in paleoclimate among the rocks layers that we'll see from older to younger. Here's one of the coals along the Great Allegheny Passage. There are a few of these exposed to view. This is west of the area where we'll cycle in the peak of the passage, but these are around. This one's not especially thick, and they were mined both in surface mines and the subsurface, even when they were only maybe 3 feet or so thick, sometimes even thinner than that. So they didn't have to be super thick to be mined, even in the subsurface. This is the thickest and most extensive coal in the region, and this is a focus of part of the talk in the plateau theme. So if you want to learn more about the Pittsburgh coal, check it out in there. The map here shows where this coal is thick and of good quality. It's been mined where it's red here. It's still present when this map was made in 1997, where it's the medium gray. And it's actually, this is an old map 25 years ago, but it's still present in much of this area. And again, you'll see that in the plateau talk. So it was first mined, here's Pittsburgh, first mined on Mount Washington here in the mid 1700s. And then mines worked their way back from the outcrops along the Monongahela River, outcrops along the Ohio River. Mines worked back miles away from those outcrops. And then there are mines that came down from the surface too, where the rock was more deeply buried. So a very important resource. It's 6 feet thick on average over a huge area here. It's even thicker in this direction. And the rocks, the coal here was especially good for making coke. The Connellsville Coke District was over here. So away from that area of pretty continuous coal, you can see there are patches where Pittsburgh coal has been mined. And those are patches of rock of Pittsburgh coal age that are preserved in the low parts of folds that we'll talk about later. In between those, the rocks at the surface are older than the Pittsburgh coal. The Pittsburgh coal layer was there at one time, but has been eroded away and it's gone now. So here's another patch where it's present. This is a low fold that goes through Berlin in Somerset County with Middle Pennsylvanian age rocks. Going through Wellersburg here in Somerset County, there's another downward fold. There's a little patch of Pittsburgh coal here near Wellersburg that was mined, and a bigger area in the same downward fold down in Maryland. This is the Indian Creek Valley Trail gorge that will cycle. And the upstream part of Indian Creek, if you drive along the highway there, you'll see evidence of mining. There's acid mine drainage from both, there were both subsurface and surface mines of thinner, older coals than the Pittsburgh coal. And there's been successful mitigation of that along Indian Creek. It's a great thing. You'll see the settling ponds to mitigate the acid mine drainage so that the water flowing through the Indian Creek Valley here is a lot cleaner than it would be otherwise. And there are places where there's been mitigation like that elsewhere here, but there are still places where the acid mine drainage flows freely. And you see a couple of those along the Gap Trail, not in the peak of the passage area where we'll cycle, but much farther to the west. The so-called Red Waterfall, it's orange really, is a well-known feature along the Gap Trail, right next to the trail. And it's the water there flows over a coating of iron oxide that's precipitated out of the water. That's why it's orange. And that's acid mine drainage. To the west of that, there's a White Waterfall, a similar feature. It's also acid mine drainage, but it's precipitating aluminum oxide. So sometimes they're orange most commonly, but sometimes those are milky white in color from aluminum oxide. And again, there's more about acid mine drainage and coal mining in the Conemaugh Uplands talk in that theme. Now let's talk about the shape of the land, and we'll start off with a pretty big picture here, a big area, and then we're going to zoom into finer and finer scale, the area of interest, especially to us. Again, elevation reds are higher elevations, the greens are lower. Here's the coastal plain in Maryland, Delaware, and New Jersey. The sediment at the surface here is relatively young, maybe millions of years old, even tens of millions, but relatively young, not super hard or well lithified. Sea level has been both higher and lower than today, and it's a pretty flat plain, this coastal plain. Similarly, along Lake Erie's been both higher and lower than today. And so there's a veneer of beach deposits on top of bedrock, as well as a veneer of deposits from glaciers before they retreated in this lake plain area. But in between the coastal plain and the lake plain is an area where the ridges, the valleys, the shape of the land have everything to do with the underlying geology. The area of Pittsburgh here was once buried something like 8,000 feet deep, and the rocks, sediment on top have been eroded away, carried off to ocean basins. The rocks here in southeastern Pennsylvania in the Piedmont and in the Piedmont of Virginia, those rocks were largely once buried something like 30,000 feet deep and became metamorphosed crystalline rocks. And there are igneous rocks, crystalline rocks too, that cooled from magma at great depth and formed large crystals like granites. So those crystalline rocks were once much deeper, were thrust up by that continental scale collision between Africa and North America. And then a mountain belt was here, once as high as the Andes, that's now worn down to its roots. So those rocks that once were buried very deeply are now at the surface. There's some other sedimentary basins in here that are younger that we'll talk about a bit later. And in between that area, if you go to the west now, you can see these long ridges and long valleys, very fine, narrow ridges, long valleys that go way down here. This is a continental scale feature because it's from that continental scale collision. That's the Valley and Ridge geographic province of Virginia, or Ridge and Valley province of Pennsylvania. Again, the root of this ancient mountain belt. And this is where rock layers, sedimentary rock layers, were intensely folded and now worn down to their roots. And you'll see some of the details of that. In front of that area of intense folding, there are some broad folds. You can see these broad folds in this area of a high plateau. And then the low plateau, the rock layers are relatively flat lying, and streams and rivers go every which direction. They don't have a preferred orientation of drainage like the rocks in the Valley and Ridge province. So you can see that these provinces go over a pretty big area. I'll also mention the Smoky Mountains because you won't see that on later slides. Again, crystalline rocks here, mostly metamorphic, maybe some igneous rocks too. No real preferred orientation of drainage in those crystalline rocks. And the trend of those old metamorphic rocks that were thrust up and then erosion exposed them to view That trend is the Blue Ridge in Virginia, and it goes into Pennsylvania too. And it, together with the Great Valley underlain by limestones and shales forming a valley, that trend goes off into New England. So you can see that these are regional scale features that we'll be focusing in on now as we focus in our area of interest. A closer view, then there's Pittsburgh, the low plateau, relatively flat lying rocks. This is an upward fold, that's Chestnut Ridge. A downward fold, Ligonier Valley is in that downward fold. So is the town of Ohiopyle. And then another upward fold, that's Laurel Hill. And there's a series of folds here too. The intensely deformed fold belt in the Valley and Ridge province. And the Valley and Ridge, or the fold belt, they're separated from the plateau by the Allegheny front. You can see that really clear separation, a fundamental change in the nature of the landscape across that. And another name for that, Allegheny front, or this is Allegheny Mountain. And the Conemaugh River cuts through these folds. There's gaps there for the Conemaugh River, and the gaps in the edge of the Allegheny front, those combined were used for early transportation across this area by railroad. And that's another theme that's in the Conemaugh Uplands talk. The Youghiogheny River cuts through these two ridges, cuts through Chestnut Ridge and Laurel Hill, and forms a gorge there. And again, you'll see these ovals indicating the two areas of the ride, Indian Creek and the Peak of the Passage. So this landscape has everything to do with the geology then, the underlying rocks. These ridges are held up by quartz-rich sandstones, resistant to erosion, like we talked about before, and the valleys are underlain by shales that are clay-rich and limestones, easily dissolved. So those are the valley forming units. So the landscape here has everything to do with the geology. And these ridges are held up by quartz-rich sandstones as well. Here's a close-up of Youghiogheny Gorge going from Connellsville here to Confluence, cutting through Chestnut Ridge and Laurel Hill, Ohiopyles in the town of Ohiopyles in this valley in between. There's the location of Indian Creek. And people who've looked at the gorges in Pennsylvania have measured that the Youghiogheny River Gorge is the deepest of them. It's a little bit deeper than beautiful Pine Creek Gorge, which has a wonderful bike path in it, deeper than Conemaugh Gorge that we talked about in the Conemaugh Uplands talk. So the deepest gorge in Pennsylvania. Now let's look at the geology behind those landscapes and those landforms. The colors on the map here, this geologic map, the colors indicate different ages of rock. It's not rock type, but different ages of rock, from younger rock layers in the plateau here in Greene County in green to older rock layers, they're Pennsylvanian in age through here, even older rock layers, Mississippian, and then northeastern Pennsylvania, Devonian age rock layers. So generally younger to older sedimentary rock layers. These are Chestnut Ridge and Laurel Hill, and you can see that in the cores of those upward folds, there are older rocks exposed. So there are Mississippian rocks exposed in the cores of both of those folds. And in the downward fold in between and on the flanks, there are younger rocks preserved. So this is cross-section DD prime. You can see the depth of the Marcellus here, about 7,000 feet. There's no squeezing of this section. It's a one-to-one lateral to vertical scale. So the lateral scale, 7,000 feet, is about the same distance as the depth of that green arrow. And you can see that in the low plateau, the interpretation is the rock layers are pretty flat lying with some small structures. There's the bump up, the upward fold, that's Chestnut Ridge. There's the one that forms Laurel Hill with those sandstones armoring it and making it resistant to erosion. We go through more of the high plateau, and here's the Allegheny front. So on the geologic map, the Allegheny front is this profound change in the geology, just as it was a profound change in the landscape. And here you can see the folds in the fold belt. There's interpreted to be a deep detachment and a weak shale. You can think of this detachment like a rug on a hardwood floor. If you push the rug up against a wall, the rug will start to buckle over and over and buckle against itself. and maybe make shapes similar to these shapes. And remember, this is the edge of a mountain belt that's worn down to its roots. So once there would have been additional detail above this. So it's the root of that. There are some pretty old rock layers at the surface and rock layers of many different ages. That's why it's such a complex pattern through here. And some of the old rock layers that are at the surface in central Pennsylvania in the fold belt, they're well in the subsurface in the plateau and don't come to the surface. And the Allegheny front is where that deep detachment is interpreted to rise up and become a shallower detachment. And you lose the amplitudes of these folds. The folds are smaller. You're getting away from the locus of deformation in the contact between the continents. A couple other features of this, I mentioned metamorphic rocks off to the east in southeastern Pennsylvania. You can just see a little bit of that in this cross section. Those are the metamorphic rocks that are on trend actually with the Smoky Mountains and the Blue Ridge. There are more metamorphic and igneous rocks back here, crystalline rocks that are really old and were formed really deep beyond the end of the cross section. But I wanted to point out the green area both in the cross section and in the map. So after the mountain belt had largely worn down, the assembled continents started trying to rip apart. And there were pull-apart basins formed with sediment pouring into those basins and filling them in. So that sediment filling in this pull-apart basin, like an East Africa rift basin would be an analogy to this. It's colored green in the cross-section and on the map. And with all the natural fractures and the faults that were being formed, it was easy for magma to come up and intrude those sedimentary rocks. And that's what's shown in red. They're igneous rocks that intruded these younger sedimentary basins that post-date the mountain building episode. So there you have it, a thumbnail sketch of the geology of Pennsylvania. Hopefully you can see that these folds in the plateau continue all across Pennsylvania well into northern Pennsylvania. They're not just in southwestern Pennsylvania here. The landscapes in the low plateau, as I mentioned, are having these streams go every which direction. But notice that the stream valleys expose older rock layers in the core of the valleys and younger rock layers up high. So that's a theme in the plateau. These thin red lines, probably hard for you to see. That's the maximum extent of glaciations in the last couple million years or so. Glaciers came into northeastern Pennsylvania as well. And those will be a topic of the glacial theme, another one of these talks. Here's a more generalized geologic map of Pennsylvania. Again, you can see younger rock layers at the surface here, although they're hundreds of millions of years old, going through Pennsylvanian, Mississippian, into older rock layers, Devonian. And as I mentioned, when you cross the Allegheny front here and get into the ancient fold belt, there are some very old rock layers exposed at the surface. This one shown in purple, Silurian age rocks, includes that really quartz-rich Silurian hard sandstone that's a ridge-forming unit that I talked about earlier. The Ordovician has lots of limestones, like the one I mentioned that's good for agriculture, as well as shales, tends to be a valley former. This is the Great Valley that we saw in those elevation maps previously. Here's our area of interest with these two rides in the Laurel Highlands. We're going to focus in on a little snippet in southern Bedford County and look at a satellite image there. And then we're going to look at a satellite image over a bigger area that includes the Peak of the Passage ride. So this is to establish the relationship between the geology and the landforms. So here's a satellite image of much of Pennsylvania. And here in southern Bedford County, we're zeroing in. And you can see these long ridges. They're held up by Silurian quartz-rich sandstones. And this is Ordovician limestone, an older rock unit in between. So this is an upward fold. These are the same rock layer on both sides, Silurian sandstone, with a core that's eroded into an older rock unit, this limestone that's so great for agriculture. And then going away from on the flank of that upward fold, you can see you get into younger rock layers and eventually into Devonian mix of rock types like we talked about on the cross section, shales, sandstones, and thin limestones. The land use here is affected by the geology, not just the shape of the land, but the use of it as well. The soils on the Silurian sandstone are thin, not well developed, not great for agriculture, doesn't have the buffering qualities of acidic decaying plant material that limestone naturally has, as well as limestone has natural nutrients, so that you don't need to use as much fertilizer on it as soils based on other rock types. And you can see not wall-to-wall croplands here, so a different land use because of that different underlying geology. And if you go on the other side of the fold, you see this valley, and you might guess from this which rock unit this is on the other side of the fold, and it would be this rock unit with a very similar land use. So now that your eyes keyed in, I think you'll be able to look across Pennsylvania and Virginia and pick out these valleys that have lots of this Ordovician limestone at the surface, near the surface, limestone-based soils that are wall-to-wall croplands. So the land use and the landscapes have everything to do with the geology. And then the ridges here in this part of central Pennsylvania held up by that quartz-rich Silurian sandstone. There are other ridges, like the ones we talked about, Chestnut Ridge and Laurel Hill, that are held up by quartz-rich sandstones, maybe not as quite as quartz-rich as the Silurian one, but still enough quartz in them to hold up ridges. And we'll look at a series of those. And I mentioned before the Great Valley. Here's the Great Valley in a satellite view. So hopefully you can now go to lots of different areas in western and northern Pennsylvania and get some understanding of the geology just looking at a satellite image. We'll look at a bigger area now. This is the area we were keyed into before with the Ordovician limestone soil, the Silurian sandstone upward fold here. It's actually split into two folds. You can see a broad fold here and one that has a fault actually interpreted on it. So it's sort of half of an upward fold. And then a downward fold, another upward fold with Silurian sandstone. The core of it is breached up here. And then some ridges over here too in the area where we're going to be cycling. There's Meyersdale. So there's a pair of ridges here and there's a pair of ridges there. And those include Mississippian and lower Pennsylvanian sandstones that are relatively resistant to erosion. If you look really closely, I think you'll be able to get an idea that the rock layers here are actually tilted down. And if that's a little bit hard for you to see, you're going to be able to see that in more detail. There we go. And to give you some confidence in what I was just talking about, here's a little part of a larger geologic map in that area in southern Bedford County. And the purple here is Silurian sandstone at the surface. These are older rock layers. There are some sandstones in those too, but this one's especially resistant to erosion. And what I'll explain next is what this symbol means. So I'm going to leave the slideshow and just talk with you directly here for a minute. So picture this as a sedimentary rock layer that's laid down horizontally initially, and then it gets buried, turns into harder rock, and this continental scale collision happens, and the rock layer gets tilted. It's part of a fold and has a tilt like this. And a geologist would come along and want to represent this on a map, this tilt. So the way they would do that, they would have a horizontal line that represents the horizontal on this tilted plane, and then a line that's going straight downhill. And two lines form a plane, so that's all you need to define that this is a plane. And this is the kind of symbol that's used: a long line that's horizontal, and then one that goes straight downhill, along with a number that's how many degrees the rock unit or the rock layer is tilted relative to horizontal. A few degrees here, a lot more degrees there. So that's the kind of symbol that's on that map. So let's go back to the map now, and you'll see those symbols. So there they are, and the geologist probably walked up or down Rainsburg Gap here, the town of Rainsburg's just up here in the agricultural valley, and took these measurements of the tilted rock layers, and with the degrees below horizontal that they're tilted down in this direction. So those are those measurements. Here's my generalization of those based not only on the geologist's observations, but what you can see in the satellite image too. that you can see these rock layers. And here's the whole geologic map that that person created. And you see there are lots of colors on here for different rock layers, lots of detail in it. I'll just point out the Silurian sandstone here. Here's that upward fold. That's the broad upward fold that had the Ordovician limestone in it to the north. It's split into two upward folds, as I mentioned. This is that upward fold that was to the west. And in between, in the valleys, there are lots of different ages of rocks at the surface. And notice how these rock layers are a bit repeated between those different valleys. And we'll look for that when we look at a satellite image of this area again. And you'll see that the land use in those valleys is also repeated. Another part of this illustration is the cross sections at the bottom. So these are cross sections of the earth interpreted from the surface geology, taking those measurements of inclinations and ages of the rock layers and interpreting these upward folds and downward folds and some faults too. So there's an interpretation of the subsurface based on looking at the rocks at the surface. Okay, so we've added some more of these symbols. So these were inclined down away from the core of this upward fold. There's another upward fold, rock layers inclined down away from that. And here, as I mentioned, I hope you can imagine that there are sedimentary rock layers, sandstones, that are tilted down in this direction. And so there's the symbol for those. And we'll actually look at a photograph of rock layers that are tilted shortly. So you'll get even more confidence in that. Those same two rock layers, groups of rocks, are over here. See how there are two ridges here as well? And those also are Mississippian and Pennsylvanian age sandstones that are tilted down in the opposite direction, tilted down to the east this time. And those rock layers, you can trace them here. They go off to the north, they wrap around and come back to the south. And here they're dipping back to the west again. So this is a downward fold, the core of an upward fold. And I hope you can picture that. But just in case, here I've shown a schematic cross-section of a rock layer in cross-section that's folded, an upward fold with those symbols on the flanks. And then here's a symbol showing the axis of that upward fold, and then a downward fold with symbols. And here's the axis of that downward fold in a slightly more golden color. So yellow, upward fold, golden, downward fold, upward, downward through this area as we've talked about as we developed this map. This is the town of Wellersburg. So this downward fold is actually named Wellersburg. Syncline is the name for the downward fold. This upward fold is called the Deer Park Anticline. Anticline is the name for the upward fold. And there's where there was a coal mine. I think Pittsburgh coal, as I mentioned, there was a little patch there. And there's more Pittsburgh coal farther south in Virginia in this downward fold. Look at the land use here too. So like we talked about for the Silurian sandstone ridges, forest on these sandstone ridges that are different younger ages than Silurian, Mississippian and Pennsylvanian. Some agriculture here, but certainly not wall-to-wall crop lands like in the Ordovician Limestone Valley. More agriculture here in the valley that includes Berlin. That's that downward fold I mentioned before, includes Pittsburgh coal. There has and is coal mining in this area, but also these middle Pennsylvanian rocks, same age as some of the rocks in Washington County, are pretty good for agriculture. Remember, there are those thin marine and non-marine limestones in that part of the section. So maybe not as great for agriculture as this one, the Ordovician limestone-based soil, but still pretty good for agriculture. There's some Pennsylvanian rocks here too, a little bit older than those, so not maybe quite as good for agriculture, at least not right here. I mentioned the repeated patterns of land use, and I'm going to go back one so you can see that. Remember, I mentioned those repeated patterns. Look at the shapes and use of the land in these areas. So I think you can easily picture the repeat of the same sedimentary rock layers in the low parts of folds through those valleys. Okay, I promised you a chance to actually see the rock layers along the gap trail, and here we go. These are pictures. There's the gap trail, and they're all facing to more or less the northeast. The sun is behind me taking these pictures. There's my bike for scale. And here's an outcrop not far from Meyersdale. These are Mississippian Pennsylvanian sandstones, originally deposited horizontally, but now they're tilted down to the west because of that folding and deformation, that compression from 300 or so million years ago, and younger. So tilted down to the west. Here's another one. This time the shales and sandstones are mostly red. So this is Upper Devonian in age, not Pennsylvanian, Mississippian, but again, tilted down more or less to the west. And then here farther east, this is just past the eastern side of the Continental Divide portal. You'll see these red sandstones and shales tilted down to the east this time. So similar age rock layers as those, Devonian in age with lots of red beds, but now tilted down to the east with the axis of the upward fold in between. The last picture here is showing a bit of the eastern portal of the Big Savage Tunnel. And again, you can see sandstone layers here. These are the sandstones that hold up Big Savage Mountain and are resistant to erosion. And they're tilted down to the east. So on the flank of that upward fold, and also the flank of the next downward fold to the east. So those are things we'll be able to see when we're cycling. And here's a summary of some general rock ages, the sandstone ridges here that I mentioned, the Devonian rocks in the core of the upward fold. And we've talked about these ages of rock layers as well. So we'll get to see those when we cycle on the Gaff. This is heading west away from Big Savage Mountain and the wind farm that's there. And there's a little section about energy resources in the plateau talk where I talk about wind farm here just briefly. And this is the wind farm that you're seeing. Here's the Gap Trail. Actually, it goes into the Big Savage Tunnel here and goes underground, pops out into an overlook. But there's a wind farm here on both of these twin peaks. And you can see to the west, you'll see these windmills from the Gap Trail. The Gap Trail comes through here. And you'll see these in the same age rocks that also form a ridge here. So the wind resources, the ridges that are high, have everything to do with the underlying geology and the sandstones that hold them up. Now we're going to come back to this great overlook that we talked about earlier, just past the eastern end of the Big Savage Tunnel. There's a view on a pretty clear day from there. It's really the most expansive view on the Gap Trail. And now that we've talked about the geology, I'm going to identify some of these features. There's Wellersburg, PA, in the core of that downward fold. There would be the other ridge over here of Pennsylvania and Mississippian sandstones on the other flank of that downward fold. Here's a line with no trees. That's the Pennsylvania-Maryland state line. And in the far distance, I'd wondered what this was for years. I finally, in making this talk, looked into what that is. And that's a mine that we'll see a closer view next. And this is actually the Narrows. You can almost see Cumberland, the end of the Gap Trail, from this overlook. And I'll try to convince you that that's the case with the next illustration, which is a 3D perspective view of that area. So there's that mine that you can see from the overlook. It's part of a complex of mines here. Mines really focused, I think, on limestones of lower early Devonian age and late Silurian age. So not ages that we've talked much about before. And I think for largely for making cement, but so clearly a mine on the flank of this ridge. This is Will's Haystack Mountain. It has two names, Pennsylvania and Maryland. And can you guess what rocks are holding up this ridge? And if you guessed Silurian sandstone, you would be right. And this is Will's Creek that cuts a gap through that upward fold, that sandstone ridge. And the Great Allegheny Passage Trail follows along on the right-hand side of Will's Creek here, entering into Cumberland, and the end of the Gap Trail and the start of the Great Allegheny Passage. You can see the Potomac River there flowing next to Cumberland. So you can see the Narrows from the overlook and almost see Cumberland. We talked about interpreting the subsurface layers and faults and folds based on the surface geology, but let's look at a direct image of the subsurface. And to do that, we're going to look at some images made from sound waves, and there'll be cross sections of the earth that are vertical sections, but this is what they would look like in map view. The two that are highlighted in blue cross each other. There's one that's highlighted in dark red on the next slide, and they cross from the low plateau into the high plateau. They don't quite get into the fold belt though. So those are the images that we'll see. Here they are. The two blue ones, as I mentioned, they cross each other. High plateau to the right, low plateau to the left. And then this is the red, longer one that has both high and low plateau. And the way these are made is there'll be a source of sound waves, like a thumper truck at the surface, that sends sound waves down. And where there's a big change in rock type, like shale to limestone, for example, some sound waves will bounce off. Some will continue through, but some will bounce off. And there are really sensitive sensors at the surface that measure the time it took for those to come back. And so this axis is actually two-way travel time. It's 4 seconds to the bottom here in two-way travel time. But there are wells in this area, and we can use measurements in the wells to establish a tie between the reflections on this acoustic cross-section and horizons or rock units of various ages in the wells. So we have some confidence the ages of the rocks that are represented here, and the different sedimentary rock ages have different colors. So that's how this is made. The scale of it is, there's the depth of the Marcellus in the low plateau, so that's about 7,000 feet deep. And the lateral scale, this is 1 mile on each of them. So these are highly squeezed, unlike the other cross section that we saw, but this time it's a direct image of the subsurface instead of an interpretation. And you can see the flat-lying rock layers in the low plateau, and then in the high plateau, these broad folds like Chestnut Ridge and Laurel Hill, and the others that we saw to the east of there. And they don't quite get into the fold belt, as I mentioned, which is even more intensely deformed. So there's the edge of the high plateau and those big folds, and then the low plateau with generally younger rocks at the surface and not as deformed. One of the details on this, there's some rumpling of this layer and not so much down deeper. And I've seen this on other acoustic images in the plateau too. This is a layer of salt of Silurian age that's weak where it's buried deeply in the subsurface. And that's that younger detachment that the deeper detachment rises up to right at the level of the Allegheny front, at least in many people's interpretation. So there you have some direct images of the subsurface to go along with interpretations based on surface geology. Now let's look at this other special topic, evidence for flowing water currents that you can tell by looking at sandstones in outcrop. And I'm going to start this by suggesting that if you can't quite picture this, go ahead and look for this YouTube video. It's a video of, there's a trough of water here. The water's flowing from left to right with a little sand at the bottom. It's a couple inches of sand or so. So it's just a little ripple. And the water flows across the top, the sand grains bounce along across the top, and then they avalanche down the front of this, and that keeps happening so that this thing has grown from left to right through these inclined avalanches of sand, and it's formed a lamination here, a cross-lamination. That's an indication that the current was flowing from left to right. There's actually erosion on the top here, so those laminations come up and are abruptly terminated, and sometimes these laminations can come down to the base here tangentially, and we'll see that in some real examples. There's flow is turbulent here. That's part of the reason that the sand grains drop out, and there's also erosion here on the top of the previous bed that contributes to the abrupt termination of the laminations on the top of that previous bed. So again, I encourage you to look for this YouTube video if you can't quite picture that, and I think that may help a lot. And these can happen at all scales. This can happen for sand dunes that are blown by wind in a desert area. You've seen these in rock layers if you've gone to Zion National Park, these huge inclined laminations, 100+ feet high. They're in Capitol Reef National Park too, or small scales like this, maybe an inch or just a fraction of an inch, or scales in between. And they can be formed by water flowing like this one, or as I mentioned, by wind. So here's a really great example of one of these right along the gap trail. This is to the west of the peak of the passage where we'll cycle, but it's worth showing anyway. And it's a pretty large crossbed set, these cross laminations. You can see them coming down from left to right, indicating the water that deposited this rock was flowing from left to right. This rock has marine fossils in it, so it surely was deposited in a shallow sea that covered this area in Mississippian time. This is that Loyalhanna limestone that I pointed out on the rock diagram of Pennsylvania. It was blue on that. It's weathered out in relief. Probably these layers have more quartz grains in them, and these layers that are weathered back have less quartz and more carbonate. It's a mix of quartz sand grains and also carbonate in this rock. Here you can see the top where they're abruptly truncated, the tops of those laminations. You can see them coming down tangentially at the base. There's another crossbed set. You can see the laminations incline down in the same direction with my pike for scale. Here's another outcrop along the gap trail of Loyalhanna limestone. And again, you can see these cross laminations in the flow direction, left to right here, but here, right to left. And maybe actually the flow orientations were kind of obliquely into the outcrop here. You can't really tell that from this. But if there were bidirectional flow directions like this in a shallow sea, that could be from tidal currents. Ebb and flood tidal currents flowing in opposite directions. So that's one potential interpretation of having opposing current directions, at least apparently, in this outcrop. There's another example of outcrop of Loyalhanna limestone. This time it's a very fresh outcrop in a mine. There's a vehicle for scale, and you can see these inclined crossbeds. I hope you can see those in this rock and indicating flow direction this way. There's another crossbed set above it, indicating a flow direction the other way. And because this is a limestone where it's near the surface here on Chestnut Ridge, it's had groundwater come into it and dissolved away some of the limestone and formed Laurel caverns. So Laurel caverns are in the Loyalhanna limestone. This natural fracture was probably a conduit for water here that made a long passageway along that natural fracture down in the underground. And probably you've already noticed the lamination here. And yes, you can see cross lamination in the Loyalhanna limestone inside Laurel caverns. The Loyalhanna limestone is an economically and regionally important rock unit because it makes an excellent building material for roads. When you break it, crush it into gravel or riprap, the surface of it's really rough. Those quartz sand grains stand out in relief. It feels like sandpaper, and it's a pretty hard and durable rock too. So it makes a great construction material. And so it's mined along Chestnut Ridge here. You can see Chestnut Ridge and some surface mines here. There's a close-up of one of them. This is Laurel Hill. There's Seven Springs and Hidden Valley. And along the crest here, also there are surface mines for Loyalhanna limestone and some sandstone units that are used in construction, as well as subsurface mines for Loyalhanna in the Highlands here. The portals of a subsurface mine in the Loyalhanna. And here's a map of that subsurface mine. It's a room and pillar mine. The gray areas have limestone removed. The white, it's left behind as a pillar. We talked about mine types in the Conemaugh Uplands talk. So it's such a valuable resource. It's even mined underground as well as above ground. And in facilities where it's crushed into gravel, the fines that are left over, often those are used on rail trails. So a lot of the fine crushed limestone gravel that we cycle on is Loyalhanna limestone. And we'll see a lot of this on our bike rides because it's such a common material used on trails and roads. It's kind of all over the region and a really valuable material. Well, I'm afraid I've spoiled you by looking at really large crossbed sets in the Loyalhanna limestone. So I wanted to show a smaller one. This is a sandstone that's in place. It's Mississippian or Pennsylvanian sandstone, not far from Meyersdale, right along the Great Allegheny Passage. And I hope, having looked at this for a few seconds now, you can already pick out these inclined laminations abruptly terminated at the top, coming down tangentially to the base, indicating flow from right to left. And that's consistent with the river direction we saw on that map of ancient rivers 300 million years ago in the Pennsylvania, going across Pennsylvania more or less from east to west. And I think this is from a river sand deposit. So we'll see lots of examples of these, not only in these two Laurel Highlands bike rides, but also in other places. And we'll make a rest stop at the Deal parking area. And between the parking area and the trail are some rock barriers. They're just great. They're gray limestones, but also there are cross-bedded sandstone blocks. And we'll have a little competition or contest in identifying which way was up on those based on the cross laminations, these tangential versus abrupt terminations at the base and top of the crossbed sets. So I hope we've met our objectives of increasing your awareness of the link between geology and landscapes throughout Western Pennsylvania, Northern Pennsylvania, including in the Laurel Highlands, and that we've given you some background on the peak of the passage and the gorge part of the Indian Creek Valley Trail. And again, this is one of a series of these talks. There are 25 great trails out there for you to visit. We're not, sharing this to sell trips with Venture Outdoors. We're sharing this to encourage you to get out on your own with your friends and explore these great trails. And to, if you watch the videos, more of the videos, just to get a little more background about why the region around us looks the way it does, and a bit of the history too. So I hope to see you out on the trails, and all the best to you.